lecture about generalized Jarlskog Invariants. So I hope I pronounced that correctly. And if anyone wants to stop the recording or tells because they don't see something on the board or it's unrecognizable, please just feel free to unmute and ask Klaus to write it better.
Yeah, in fact, you're welcome to unmute yourself and also ask questions. So we will try to be slow, and so it should be accessible to everybody. Good. So yeah, so it's generalized Jarlskog invariant mass degeneracy and the Echelon cross. If you haven't heard of Echelon cross, that's because that's a word I have invented. But the other two, you might have an idea of what this is about. And this is inspired by the standard model. So in the standard model, there is a term in the Lagrangian. Of course, the standard model Lagrangian is famously more than a t-shirt. So, but we will just look at the relevant terms. There will be a term here. Okay, so you should speak up if you cannot see it. And I hear nothing. So D bar L, oh, it should be MU, of course, MU, and then L, U, R, and it should be I, R, and then there's another term also with minus M, A, D, D bar L, A, D, A, R, and then plus Hermitian conjugation. So we have, and there should be a bar here, I guess. So we have some spinors, and then we have the famous CKM matrix, which is Cabibbo-Kobayashi-Maskawa. Have everybody heard of that, or should I write out the names of these people? It's okay. Good. So the point is that the central object of today's lecture is this matrix, and so I use I for the up type quarks, and I use an A for the D type down type quarks. So the point is, in the standard model we have three generations. So the up type quarks are the up and the charm and the top quark, and the down are down and strange and bottom. And but we call them all up and down. And then I want to generalize this to not just have three generations, but maybe have n generation. And here I have written it in a mass basis, and I could, in principle, so this is the mass terms for the up type, and here's the mass terms for the down type. And then there could be degeneracy. So mass degeneracy means that the masses here could be the same for different generations of quarks. And as I write it here, we could actually generalize this to a non-square matrix, to rectangular matrices. That it's not guaranteed it will make sense in a physical model, but at least it would make sense for what I want to discuss next, and that's the symmetry, the flavor symmetry of this model. And so let me write mass matrix. So I'm just going to write the up one. There's of course also going to be a down one. So this would be the diagonal matrix of the up masses here. So this would be some matrix in NU. So I call the number of up quarks for NU and the number of down quarks for ND. So this would be a matrix that lives here, a diagonal matrix here. And there's a similar matrix for the down one here. Is this clear? And then we want to introduce a symmetry which is preserved by this in this case, and this will be all the unitary matrices U NU such that U commute with the mass matrix MU here. So the point is that we can apply symmetry transformations on this matrix V, and the way we're going to do that is we would have, say, a V prime, which should be equal to a unitary up matrix V, and then a unitary down matrix dagger here. So there will be unitary transformations, but the Lagrangian would not be invariant under such general transformation, because the mass would be are in general different. There would be this, if all the masses would be the same, then it would be invariant. But in general, the masses are different, and then there will be a smaller group that would still be a symmetry. So the smaller group will be the matrices, the unitary transformations that commute with the mass matrix. Does that make sense? And in general, of course, this would be, I mean, in the case that all the masses are different, then the unitary matrices will go down to only being U1 phases. So in general, this group here will be a product of unitary factors, of U factors. Are you with me so far? And I should of course also say that the way the unitary matrices act on the spinors here, that's just in some fundamental representation of the matrix. So the point is that we insert U matrix in D, for instance, here, and then it would act with U dagger on V, and so on. So in general, there will be that the U left right I would prime would be like the U matrix, and then there will be U left right acting on that. I can put indices on, then it will be like I, and then it will be I, J, J, and so on. And here, if I put indices, then it will be like I, J, J, A, B, and then I guess it should be B here. Does that make sense? Okay. So that's the first thing. So now to the main fact. Of course, now I will define an equivalence relation, where I would say that two matrices are equivalent if there exist two matrices U in the remaining symmetry group GU and another UD in GD, such that they're given by this transformation that V prime is equal to UU VUD dagger. So there will be some equivalence relation. And now we get to the main point, that the fact is that there's no CP violation, if and only if V is equivalent to a real matrix. So this is the fact, and then from now on we want to generalize this. Of course, V in the standard model is a 3 by 3 unitary matrix, but since we want to generalize away from quadratic matrices, we have to give up that V have to be unitary. It doesn't exist for rectangular matrices. So we will simply just say that V should be any complex rectangular matrix. And then the question, but we will then ask the question, is it possible to, by unitary transformations, the reduced unitary transformations that commute with the Mars matrices to make V real? This will be the question we will try to answer. And so first I have to say something about unitary matrices. So if we have a unitary matrix, then typically we can think of a unitary matrix as e to the IH time of some symmetric real matrix, and then O, where O is an orthogonal matrix. So the point is, so U, say U belongs to UN, and O belongs to ON, and this H is a real and symmetric matrix. So we can parameterize any unitary matrix in this way. You probably know that the dimension of the unitary group is n squared, and the dimension of the orthogonal group is n minus 1/2. And it's not difficult to see that the number of real symmetric matrices are n plus 1/2. So this actually makes sense dimensionally. And the point is, of course, that does everybody know this? Or you want to see in more detail why this is the case from group theory? So I mean, the point is basically that you think in terms of Lie algebra, and the Lie algebra of the orthogonal group is the skew symmetric matrices, and the number of skew symmetric matrices are precisely given by this number, and or anti-symmetric matrices, and the number of real symmetric matrices is given by this number here. And another thing is that this is by Jarlskog and collaborators. Then they typically call this Euler angles, and they call this phases. So these are complex. So the point is that a unitary matrix is, roughly speaking, given by n plus 1/2 complex phases, and n minus 1/2 Euler angles. I see Richard is nodding. That's okay. So that's the next fact. So now, so you can still see this here. So the next point is that now we want to introduce the double commutant. And And the double commutant is the vector space that commute with our reduced group. So U will be equal to all the matrices, the real matrices, du, which are real matrices nu cross nu, real, such that for all u in our reduced group, symmetry group, they commute with du. So this is why I call it double commutant, because the group is sort of the commutant for the Mars matrix. And here we're talking about the vector space which commute with our group, which is already the commutant, so to speak. So I call it the double commutant. And then you can think a little bit about what matrices satisfy this. What vector space is this? And a little bit of thought, you realize that the only thing that can happen here is that they have to be diagonal. So the point is basically how to say this in the best way. So imagine that we have a situation where we have some masses. So let's say that the mass matrix in U have some degeneracy. So maybe these ends are the same here. So that's some blocks where they have the same mass, something like this here. And then the point is that we are trying to the corresponding group GU will be so if there's 3 here, so there will be like a U3 cross. Now I draw 3 here, so maybe let's take 4 here. Cross a U4 cross and so on. This will be the symmetry group that commute with this mass matrix. And now we want to find out which matrices commute with this symmetry group here. And the point is basically that there cannot be anything in off-diagonal blocks, because if you are in off-diagonal blocks, then you could just use the U1 factor to that can be seen. So there can only be something inside the blocks here. And inside the blocks, because there's a full unitary group, the only thing that commute with that is diagonal matrices with the same eigenvalue. So the only thing that lives in double commutant is basically something which is, so let me put it like this, it's like projection matrices. So if I write, let's say that my up mass matrix is basically some mu, then projection operator mui here. So this is supposed to be some projection into each of these subblocks. And then I probably want to write ui here. So it will be sum over different blocks here. And then what is this VU? It is a very, very complicated way of saying that this is equal to the span of the real span of all the projection operators, PUI. Does that make sense? I see Patrick is nodding. So it's actually a very simple space. Of course, in the case that we have the non-degenerate case where all the masses are different, then of course all the blocks are just 1, 1, 1, 1, and then this becomes just a span of projection, one-dimensional projection operators here. So it's quite simple space. And now we are ready to define the Jarlskog invariant. And it's defined as follows. Maybe I put it over here. So we say that it's defined with two copies of the up double commutant space and two copies of in an antisymmetric combination actually of the down here, and then it gives back a real number. This is the Jarlskog invariant, and it's defined as follows. You take matrices in each of these double commutants. So I call the matrices I and J, capital I, capital J. That's because later we see, especially in the non-degenerate case, it would just label the index, I mean the row index and so on. So I call it I and J to remind myself of this, and then A, B here, and then it's given by imaginary value of trace of I, V, A, V dagger, J, V, B, V dagger here, like this. Or maybe it's bad to call JJ, so maybe let me call this for K here, and this for K here, like that. So so this is a bunch of matrices I have multiplied together, take trace, and then imaginary value of that. And why? The first thing is, why is this invariant under the group? And the point is basically that if we change V to V prime, so that means that we put in a unitary matrix on both sides, one unit U up next to U, and then U down next to next to V and also V, and then you do the opposite with on the other side. So you of course have to put in a U dagger here. And the point is that the I and the A and the K and the B, these matrices lives in the double commutant which commute with the group action. So therefore, we can bring the unitary matrix past the I's, and therefore we see that it's actually invariant. Does that make sense? So this is the whole point. This is what this is a slight generalization of what Jarlskog invented many years ago. And so the first thing we have to see is there's some nice properties of this invariant. So, and this is probably easiest to see if we write out what the imaginary value does. So if I write it out twice, then I get this is equal to 1 over 2i, and then I get trace, and then I get I, V, A, dagger, K, V, B, V, dagger here, and then minus the same complex conjugated. I will use dagger on a U by 1 by 1 matrix. So it's like A. Well, it's not a 1 by 1 matrix, but I guess it's V, B, V, dagger here. I can get away with put this dagger here. That would be okay. That would be the same as complex conjugation here. Does that make sense? And then the point is that the way we complex take Hermitian conjugation is that we take the opposite order. So this becomes equal to V, B. B is a real matrix. It's actually a diagonal matrix, so it doesn't see the dagger. And then we get V dagger, K, A. I don't know why there's a dagger here. I guess I forgot a V here. So there was a V, and then so I get lost here. So we have here it's a VBKA. So I guess I only need the I. Is that? It looks like there's one missing.
The V should come after the K.
V here, and then an A, and then an I. Is it okay now? So this term is equal to this term. And then I can put the I can use the cyclicity of the trace to put the I over here.
With dagger, Klaus.
Yeah.
Before the I.
Oh, yes, thanks. There. And then I can use the simplicity of the trace to put the I in front of here. And then we see that this is actually the same, what is written over there. The only thing is, oh, there's also a V dagger missing here. There. The only thing that's the difference between this term and that term is that A and B are opposite. So we get the property that J is actually antisymmetric in A and B. And this is why I said that they live in the antisymmetric tensor product. Then of course I should write B and A here. And of course a similar argument shows that that it's also antisymmetric in the two first elements, K and I, and A and B, like this. I guess there should only be one minus. There. Okay. So we have these invariants, and they're labeled by 4 entries of basically of these projection operators, and they come in antisymmetric form. So this is what we have. We can say a little bit more if we know that that the V matrix is unitary. Because if the maybe I should say why did first of all, why did Jarlskog look at 4 entries? Because there's another obvious candidate I could have stopped. Why did I continue to 4? Why didn't I stop with 2? And you can convince yourself that if you repeat this argument with 2, then you get 0. That if you only use 2 entries, then you just get 0. So this is not interesting. It becomes interesting for 4 entries, and there's of course an obvious generalization to 6 and 8 and so on, where you just continue this. Anyway, we will only look at should we call it the quartic Jarlskog invariant. So now let's look at the unitary case. The unitary case, when V is unitary, then if we put one of the 4 entries equal to an identity matrix, then the 2 V and a V dagger will be next to each other. And in this case, we basically get down to, we get 0. Is that right? Yes. So the point is basically that if we take in the unitary case, okay, unitary V, if we take one of the entries to be a unit matrix, then I would then you can prove that this actually vanished. But on the other hand, you have also linearity. So therefore, this gives you a condition that if we write the unit matrix as a sum of its projections. So if we write this as J, and then the projections I, U, and then sum over them, then we get a condition, some relation between the different Jarlskog invariants in the unitary case. And you can do this for any of the 4 entries. So you get a lot of relations in this case. This will be useful in a moment. So this is basically the setting. And of course, oh yeah, and another important thing is that if V is real, then clearly the Jarlskog invariant vanish, because it takes the imaginary part. Because all the entries are real, and if V is also real, then of course everything is real, and there's no imaginary part. So if we can make the CKM matrix real by this, then we see that the Jarlskog invariant is 0. So what we would like, we hope, or what is actually true in the standard model with 3 generations is that if all the Jarlskog invariants are 0, then V is equivalent to a real matrix. And we would like to see, can we generalize, and therefore there will be no CP violation in that case, if that's true. But so we want to generalize this to our rectangular case and see how does this go? Can we also, if all the Jarlskog invariant vanish, can we then also make V real in that case, even for other dimensions? And so let's have a first look at the situation. So this is basically the question what I'm asking. Those are good. Okay, so now I will go through some examples, a first look of what's the situation of this problem. This is just a matrix problem. So let's first look at the maximal degenerate case. Max degeneracy. What can we say in the max degeneracy case? Then there is actually a single value decomposition, which says that V can always, a rectangular V can always be written by a unitary matrix times a diagonal matrix with positive entries. Actually, this is rectangular, so I should probably draw it rectangular here. So you can draw it 0, 0, 0, and 0. So this is supposed to be the diagonal, whatever you want to call a diagonal in a rectangular matrix. Maybe let me make it even clearer here. And then there's 2 unitary matrices, U and UD dagger. So there is a theorem in matrix theory which is called single value decomposition, which says that you can always take a rectangular matrix and write it as this positive matrix, a diagonal matrix, and then some 2 unitary matrices. Have you heard this before? So this answers the question in the maximal degenerate case. In the maximal degenerate case, we have a unitary. We know that the groups are unitary groups, and then we can always bring the CKM matrix, and even we can make it positive. So
So can you repeat what is on the diagonal, because it's not visible?
It's supposed to be beta equal to 0.
Oh, I see. It looked like 3, 0 to me.
Beta equal to 0, beta equal to 0, and so on.
Mm-hmm. Yeah, thanks.
Other questions? Right, so that was easy. We can also mention another case which is easy. That is, if we also know that V is unitary, then of course we just need one of the unitary groups to be maximal degenerate. I mean, either the up or the down. If one of them, then of course it's trivial. We can always make V real in that case. Okay, so now let me go to the next example. So here I will take, I imagine, just for simplicity, let's say that we have we have a quadratic case here, and let's say that there is there's two different masses, so they are split both in the up and the down situation. So I have a UN left here, and a UN left here, and a UN left here, and a UN left here. Does that make sense? And then we can ask what are how can we make this? So imagine that you have a general 2n times 2n matrix, and of course the area, the area here actually represents all the imaginary entries of a 2n times 2n matrix. Remember, we're trying to make this real, so we're asking how many imaginary entries are there? There's 2n times 2n. Should I write that number? So it's 4n squared imaginary numbers that we would like to get rid of, so we can make it real. And then we can ask how many unitary degrees of freedom do we have? And then we, that's actually what I wrote over here. It turns out that the Euler angles here, they're not useful because they're real matrices. So if we manage to make, say, V real, then the Euler angles will just rotate the real matrix. So they are not effective in making a complex matrix real. It's the phases that only helps to make a complex matrix real. So therefore, the number of degrees of freedom, so imagine that n is large, then the diagonal doesn't matter so much. So I will just be rough and say that I will draw the degrees of freedom from one factor here. Here, that would be like this. And the degrees of freedom for that one would be like this. And the degrees of freedom from this one would be like this and this here. So if you imagine that n is large and we don't have to worry about the diagonal, then we see that we are short. We cannot make all the 4n values go away. So it's the number. So this is supposed to be all the imaginary numbers, and the symmetry generators we have is actually too small. And then of course you can say, okay, there was one thing I forgot to say. That is that the group here, we have a group that acts from left on the up guys, and we have another group that acts from right on the down guys. But it turns out that the effective group that we have is actually smaller than the product group of the two, because I can have a U1 factor acting from left and a U1 factor acting from right, and it would give the same effect. So, so therefore, my effective group dimension is one less. So but of course, since I imagine n is big, I can forget about that one. Now there's another thing. Since we are here, we have we can actually construct a Jarlskog invariant. And this will become clearer in a moment, but the only thing I can do, I can only construct one Jarlskog invariant. I have to use, because of antisymmetry, I cannot use the same. I only have two entries in here and here, and I have to use an antisymmetric combination, so I cannot use the same twice. So there's actually only one possibility. So I have one Jarlskog invariant, but that's not very much when n is very big. So this is not going to help me. So I have -1 and -1 in number of symmetry generators, and from Jarlskog invariant, I'm of course assuming that Jarlskog invariant vanished, which would give me one constraint. So there would be one less imaginary number, but that's still too many. Does that make sense? So this is the moment where you see, Houston, we have a problem. We cannot make this matrix real, even if all the Jarlskog invariant vanish. And and let me give you another example. So you may say, but that matrix was not unitary. What happens if we have a unitary matrix? So let me give you another example. So let's take a unitary matrix, but go up one in. So let me go 3 by 3. So now I will do here, here. So I would have this, 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 this. So we will now assume that V is unitary. And then we will assume still we have n here, n here, n here, n here, n here, n here. So you should imagine that we have some un factor, un factor, un factor, and of course the same for the down guys. Cannot write them, and then we can start to write in how many symmetries do we have, and so on. So the number of imaginary numbers is now 9n squared. Okay, that's actually, I should actually wait with this. This becomes a little bit more complicated. But we can actually put in the number of, so let me start by putting in the number of symmetry generators. So they will be like this.
Klaus?
Yeah?
Could you move the board up a little bit? Yeah.
Better?
Yeah, better, thanks.
So this, so these diagonal blocks represent all the symmetry generators. And then how many generators, how many imaginary numbers do we have for V? Well, V is now unitary. So therefore, a unitary matrix have fewer phases. So the number of phases are actually given by the diagonal here. Here. So, so the point is basically that that the number we roughly speaking we have is roughly speaking 2n squared imaginary phases that we start from. Actually, as you probably have for pedagogical reasons written that in red. So 2n squared. Actually no, it was roughly speaking. So now here so it's half. So it's like 9/2 n squared imaginary numbers, roughly speaking. And then of course there would be and the number of symmetry generators are roughly 3 n squared here. And but symmetry generators, then of course there's the usual one factor we have to subtract here. And for here we have to subtract the number of Jarlskog invariants. And how many Jarlskog invariants can we draw here? Well, it turns out that the number of Jarlskog invariants we can make is still only one, because we are in the unitary case. And the unitary, so normally if it had not been unitary, then there would be the number of antisymmetric combinations of 2 out of 3. There will be 3 here, and there will be 3 here. There will be 9 Jarlskog invariants. But they're all related because of this property here, that when a unitary, that they have to sum up to 0. So the point is basically that if you have, say, 1, 1, 2, so the first 2 can be 1, 2, 2, 3, and 1, 3. That's the only combination. But the point is that if they share a number 2, or we can take, for instance, so yeah, the 3 here, they share the 3. So when we sum over 1 and 2 and 3, then we get 0. And the 2 and the 1, so the 3, 3 is 0 by antisymmetry, and the 2, 3 have to be minus the 1, 3. So there's only 1 left. So even in this case, there's actually only 1 left. Of course, 9 would also not be so much, but there's actually only 1. So, so here we see that we have, roughly speaking, 9 half squared faces, so 4 half, but we have only 3 symmetry generators. So in this, even in the unitary case, when we go up, we don't have enough Jarlskog invariants to remove all faces. Make sense? So this is why it's interesting. So what to do? So the next, so let's take an example for how this would work. So I'll take this away here. So this is just to get you familiar with how we can reduce. So let's look at the case where rectangular case where we have let's see, we have let's say we only have 2 non-degenerate down here. So we have a U1 here and a U1 here. But then there's a maximal U n in the up sector here. So let's imagine that we have n times 2 matrix, and the question is, can we reduce this one? And the answer is yes, and it goes as follows. First, we use a unitary transformation to make this on the form non-zero and then 0, 0, 0, 0, 0, 0. So we can always rotate the first column with a unitary matrix. So it has something here, but with 0 down there. And the next thing we're going to do is we're going to use a U1 factor here to make this number real. Okay, so we will use the U1 to make this number real. And then we are going to repeat with a unitary matrix, submatrix, which is on the form 1 and then a un minus 1 factor here. So we take a un minus 1 and then we repeat to rotate them to 0 to something and then 0, 0, 0, 0, 0. So so this is an example where we can actually make this real. So in this case, we see that, and of course there's no Jarlskog invariant because there's only 1 here. So we cannot make any Jarlskog invariant that direction. There's 2 here. That's okay. So so this this is an example where we can always make this matrix real. So so this is the type of arguments that we're going to use from now on. So now let me consider the non-degenerate case. So, and I think this will be the last section for today. So from now on, for the rest of today, I will only discuss the non-degenerate case, and then we will continue next Wednesday on what happens in the degenerate case. So there, let me write the elements, the CKM matrix elements in the polar form. So I think there's a radius, and then there's an e to the I theta I a. Here. Of course, the imaginary unit and the index I should not be confused. And then what, in this case, all the Jarlskog invariant I comma j, a comma b. This will just be listed by the row and the column index number. So in this case, this Jarlskog invariant becomes just an imaginary value of VIA, VJ A star, VJB, VI B star, and then imaginary value of this. So in this case, it is, if we use polar coordinates, it just becomes all the radius RIA, RJA, RIB, and RJB, and then there will be a sign of the differences of the thetas theta IA minus theta JA plus theta JB minus theta IB, like this. Does that make sense?
Is it the last one JB? So it's sort of symmetric. Oh. You in the sign you have I, J, I. Is that right?
Yes. So I, A, yeah. So the point is basically that the A's have to be next to each other, but that's okay because we have complex conjugates turned around. And then there's a J, the J is next, and then the B is next. So this is okay. And then the point is that the I, because there's a complex conjugate, there's an I here. So IB is negative.
What about the one before that?
That's a J.
Oh,
J.
okay. Okay, yeah, sorry, I thought that was both I and
Yeah, no, that's a J, that's a J. Okay, maybe I should have used that K. Okay, so is it clear now?
yes.
Okay, so now we get to the last ingredients in the title. So now I want to define what I mean by an echelon cross. So here, let me draw. So here I have the CKM matrix there, and let me draw one cross here that, of course, is supposed to be the echelon cross. And so here we have ND of here we have N U here down here, and so the point is that echelon cross, the B matrix of the echelon cross is something where all the entries in the echelon cross is non-zero.
Could you again pull the board up? Yeah, it's thanks.
So here, it's supposed to be different from zero, and this is supposed to be different from zero. So this is what I call an echelon cross, and of course the reason why I call it echelon, that's because I guess it's from French military, and it's something in first that goes March 1st and so into war, and it has to do with when you use matrix reduction, then there's an echelon things. So it's inspired by that. So an echelon cross is something which have only non-zero entries. So we should have one row and one column with only non-zero entries. And the idea is now that can we make V in the non-degenerate case? Yeah, so there's a theorem of which I probably should quote, which says theorem. In the non-degenerate case, and imagine that all the Jarlskog invariants vanish, and there exists an echelon cross, then V is equivalent to a real matrix. So this is what we this is the theorem, and then so this gives us sufficient. So the existence of a echelon cross is a sufficient condition to make sure that we get a real matrix. And the logic is as follows. So remember that in the non-degenerate case, we only have U1 factors. U1, U1, and so on, U1, U1, and so on. And so first, we're going to use a U1 factor to make the intersection in the echelon cross real. We can do that. And then we are going to use U1 factors here to make the rest of the column real. And then we're going to use the U1 factors, the down ones, to make the row real. So we can make the whole echelon cross real. Make sense? And then we can ask, what about this element here? So this is, let's imagine that this is I and A, and now we would like to know what happens to the element here, which is B and J. And then we go up and look at the formula for the Jarlskog invariant, which we have assumed is 0. And we see that that because we have an echelon, so the point is that the most of these elements that we are interested in is, of course, it will be this element, this element, this element, and this element. And 3 of the 4 elements are guaranteed to be non-zero because of the Jarlskog, because of the echelon. And the point is that 3 of these R's are non-zero. The only thing which we cannot guarantee to be non-zero is the RJB element here. That could be 0. And then we have a sign for all the 3 of the thetas lives on the cross. And therefore, we know that theta have to be a multiplum of pi, because we have already made that real. So the only thing theta left, that's the JB theta. That's the one which corresponds to the element we're investigating. So there's 2 conclusions. Either the RB is 0, RJB is 0. Either this is 0, because we know this is 0, or we know that this is a multiplum of pi, because sine of this is 0. And in both situations, we conclude that this element is real as well. So we see that the Jarlskog, the CKM matrix is actually real. Make sense? I see people are nodding. So this is the main theorem, and next time I will try to generalize as best as possible this to a non-degenerate setting. But this is of course important first step. So now the next thing is so now let's look at the case where so there's another theorem which says I cannot spell theorem here, which says that if the dimension of the number of rows or number of columns are less or equal to 2, then we don't even know, then we don't need the echelon cross to exist. So, so the theorem says in non-degenerate case, if all the Jarlskog invariant is 0, and if n u is less or equal to 2, or n d is less or equal to 2, then V is equivalent to a real matrix. And the proof is very simple. We simply, so let's say that there's only 2 up quarks, so it's something like this here. So there's 2 here, and then there's ND here. Then we are going to use what's it called, column permutation, to make sure that the first part here, there's no zeros here. And the rest here, at least 1 0 in each column. So it's a column here. So the point is now that this part here, it has no zeros, and therefore it has an echelon cross inside here, and then we can use the previous theorem to conclude we can make this real. Okay, but what about the other ones here? Here there could be zeros, so we don't have any echelon part here, but there's only one non-zero in each column, and therefore we can use the U1 factor to make the other one non-zero element in the column real as well. So we don't even, in this case, we don't even need a echelon cross. It works. Okay, so now let's go to an example with the 3x3 example where there's no echelon cross. So here I go 3x3. Non-degenerate, so this is an example, and a V is this, and let's go to a situation where we don't have an echelon cross, and then you can convince yourself that the only way this can happen after row and column permutations, that the diagonal must be 0. Because if in other cases you can convince yourself that actually it is a echelon cross. So let's imagine that here, and let me call the other elements A, B, C, beta, gamma, and alpha. So I have 6 non-zero elements left, and then we can ask, if all of the Jarlskog invariants in this case vanish, can we make this V real? And the point is now that if you try to construct a Jarlskog invariant, then you always make a zero. So whenever you try to take two rows and two columns, then you always meet a zero, and your Jarlskog invariant is zero, clearly zero already. So there's no information in any Jarlskog invariant. So here we have 6 phases left, and but the symmetry group is U1 to there's a U1 to the 3 from the up sector, and there's a U1 to the 3 from the down sector, but there is a common U1. So there's only 5 independent. So this is an example where we cannot do this. We cannot make this real. Make sense?
So, Klaus, is this the standard model case?
No, because I didn't say that it was unitary. This is for, in fact, exactly good point. So let's now go to, let's take the same example again, but now impose that V is unitary. So if V is unitary, then you can, the first conclusion is that the determinant of V then have to be plus minus 1, of course. No, sorry, it has to be different from 0. And you can convince yourself that when you take the determinant here, there's not, of the 6 diagonals and so on, there's not much which is different from 0. There's only 2 combinations which are different from 0. And that is the A, B, C, and the so we must conclude that either A, B, C is different from 0, or alpha, beta, gamma must be different from 0. That we can conclude because we know the determinant must be of V is different from 0 because it's unitary. So we see that we must have this condition because this is the only thing of the 6 terms in the determinant. There's only 2 left, these 2. So one of them must be different from 0. Okay, then we use that it has to be orthogonal, that the rows have to be orthogonal to each other. And you can convince yourself that say we are in a situation where these are different from 0. So that's A and C is different from 0, and it has to be they have to be, the 2 columns have to be orthogonal. Then you can see that alpha have to be 0 because else it's not orthogonal. So it turns out that there's only 2 possibilities, that either A, B, and C are all 0, or also alpha, beta, and gamma are all 0. This is the only way that you can have the columns and rows to be orthogonal to each other. And now you see there's only, so either the ABC are 0 or the other one are 0. So there's at most 3 phases, and that can easily be removed by the 5-dimensional case. So the standard model is okay. Make sense? Okay, so and then so what time is it now? It's 5. Yeah, so let me just give you one more example before we stop. So this will be relevant if the standard model had just one more generation, so 4 times 4, and we are in the unitary case. So imagine that you have example 4 by 4 non-degenerate unitary case. but let's imagine that so we know that if there's an echelon matrix, then it's cross, then it's not interesting. But let's imagine that the off diagonal is 0. So I have something like this. Like this. So the off diagonal is 0. And then we can think about which Jarlskog invariant are not 0. So yeah, first of all, how many Jarlskog invariants are there? So if we don't care about the zeros, then there will be 4 out of 2. So there will be 6 times 6. So there will be 36 Jarlskog invariants before we take into account that the unitarity would kill something. But now we have put zeros here, so therefore of the Jarlskog invariant, so I claim there will be 6 of this 36 Jarlskog invariant which are not immediately 0, and then so which doesn't meet these 4 zeros. So there will be J11212. That will be composed of this first sector here, and you can go through all of the 36, and I will write down the 6 which are not immediately 0. So there will be this. So there will be some diagonal ones, J24, 24, and there will be a J34. And then there will be 2 off diagonal, J1234 and J23. I think that's misspelling here. I guess it should be 14 here. Yeah, so these 6, I claim they're not immediately 0. So for instance, the 2, 3, 1, 4, there will be 2, 3, and there will be 1, 4. So it means these 4 elements which are not 0. But it turns out that because of unitarity, all of these are 0, because you can use this trick with that you sum up one entrance up to, when you sum over one entrance, you should get 0. But when you sum, so for instance, let's take the first one, for instance, then you could sum, so you would have something which would be J, where 1 should be like 1, 2, 3, 4. The 2, 2 is of course trivially 0, and the 2, 3, so that would be like 2, 3 here, and 1, 2. It meets a 0, and so on. So you can convince yourself that the sum have to be 0, but these 2 guys are already 0, so the last one also have to be 0. So there's no Jarlskog invariance left in this case. So now we continue with an infinitesimal analysis. So we imagine that that V is of the form e to the I h, where h is infinitesimal. And H is a symmetric real matrix, so H would be on the form here, A, B, C, D, A, B, 0, 0, 0, 0, and then it will be A, B, C, D, C, D here. So H have 8 degrees of freedom real here, but the symmetry group is in this case U1 to the 4 cross U1 to the 4 over U1. So there's only 7 degrees of freedom. So in this case, it's also it's not possible. Right. So yeah. So so I plan next. I think I will stop here because not to rush, and then next time I will continue with discussing how can we try to generalize this to the degenerate case, the echelon cross. How can we make sense of that, and give more examples. So let me stop here.
Yeah, thank you very much for the nice lecture, and please feel free to ask questions or comments or something like that.
Yeah, so if you restrict to, let's say, standard model-like situations, let's have more generations or something like that. So are the Jarlskog invariants enough to rule out CP violation or not? If you have,
So this example here shows that it's not.
that is not. So this is the 4th-generation
Yes.
case.
Yeah. So we will see next time that even in the degenerate case, the 3x3 unitary case is okay.
So the really interesting question now then is, can you find some new invariants that do the trick for at least for all the physically relevant situations?
Yeah, that's a good question. I don't know the answer to that. I did not investigate higher invariants and so on. Yeah.
Yes, I might have a similar question. So what do you think would be the trend when you would go to higher, let's say, dimensions, or from to 5 times 5 unitary or 6 times 6?
It just gets worse.
It gets worse. Okay. Mm-hmm. Thanks. Do we have any more questions or comments? So if not, I guess we can end today. And so, Klaus, will you be going to talk